first layer. The second layer is a dielectric material that normally we use as board. And the first layer is design a layer. Yeah. Remember that the sign Cooper, the dielectric, we have to change and the activate layer is assigned a layer. Once we have determined the layers, we need to create a patch with the tools that we have. Okay, this is a patch. Then remember that we use here not second point description. We don't use second point description. We use the center point that normally we put in the center of the system, and we have the width and the height. Now this is very important what we will explain now, because normally, as you see in the last class, we have to change the size of the patch. And to do directly that, we need to use variables. How do we insert variables here? Instead to put directly a size, we put a dollar and a variable. For example, we can say here $L. Then in this moment we have created a variable. Then to create a variable in Ansoff Designer, we need to use dollar with the name of the variable. In this case, I put L as a variable. If I continue directly, the software requires me the size. In this case, I let it 28 millimeters, doesn't matter. Because it's a square, I put once again in the head of the patch this $L. Okay? And you see immediately the size is exactly the same, 28 millimeters. Okay? Then as you see here, the patch is centered in the system. I mean, this point is the point 0, 0. This is the width and this is the height. Okay? In this moment it's 28 millimeters. It doesn't matter because we are going to change. Okay? Then before to continue there, we have to do the first type of antenna to determine exactly the size of the antenna. Okay? Then as you remember, we can use a calculator, okay, to determine the size of the antenna. We need to use a square patch. Frequency, I don't know, we can use the same as we use previously in the last class. Input impedance 50 ohms and voltage standing wave radio. Put 2 because it's the minimum value. And here we have the dimensions. As you remember, in the last class, the dimension was 23.1 millimeters, and the offset, horizontal offset, is 9.2 millimeters. Okay? Be ready in case my computer doesn't work. We can use the computer. You will continue going. Okay? That's nice. Then we have to change first here in project variables. Here we have the variable that we created before with 28 millimeters. But here in the calculator it says that it's 23.5. If I don't make a mistake, we put near to 23 millimeters in the last class. Then we change this value, you see the antenna is smaller, and as we did in the last lesson, we put the coaxial cable directly, this via. On the left side, in the model, you have this via, and you put as properties, you go to the lower layer, and you make the fit as a coaxial excitation. Once done this, you need to change the position of the port, the properties. In the footprint, okay. You remember the position? I don't remember. I guess it was 28 millimeters. Okay. We have to do the analysis. The analysis was in 3 gigahertz. And we need to define strip. We use from 2.8 until 3.2 because remember that the central frequency is 3 gigahertz with 21 frequencies. We use interpolating simulation and we just do. Once it's finished, we create the results. Remember that the results are the S parameters as the first result, and the second result is the impedance as a real and imaginary part. Then as you can see here, the imaginary part is near to 0 and the real part is bigger than 50 ohms. Okay? Then because the impedance, the real part is bigger than 50 ohms, we need to go to the center of the antenna. Because remember that in the center of the antenna we have 0 as an impedance. It's a short circuit. Okay? Then we need to change. Let me put the position of the fit as a variable too. And I will change directly here in project variables these variables, these values. Okay, let's simulate once again. And the result here, remember that what we need is the impedance. Look at here, it's not 70 ohms, we have here 60 ohms. Okay? And this value of the imaginary part we need to put in 0. Okay? Then we need to do 2 things. The first is to reduce the excitation position, and after we need to reduce the size of the antenna. Okay? Then here I make a mistake. The size of the antenna must be increased. Let me see. Okay. We have the position. Change a little bit. Then, as you see, if we increase the size, the imaginary part picture goes to left. If we reduce the size, the imaginary picture goes to right. Okay? Then look at here that this point, this figure, will be shifted to the right side because we decrease the size. Okay? We need a little bit more. You see, if we decrease, the picture goes to right. If we increase, the picture goes to left. Okay? Now, if you see, we are very near to 0, this imaginary part. And if you look here, we are near to 50 ohms. Then if you look at that, look at this picture, it's very nice, because the S11 parameter goes to minus 30 dB. If I want to be very good in simulation, I need to put more points. Okay? Then you can see here that we are as a central frequency in 3 gigahertz with very nice response. And here, if you look at here, you can see that there is imaginary part near to 0, but the real part is not 50, is 47. We want to go to 50. We need to move the excitation to a bigger size, because remember that if we go to the center, it's 0. If we go to the side, we increase the value. Okay? Then we can put here this value, probably we get a bigger size, a bigger value. Okay? Then we have to reduce this value. Okay. You can see here the response is better. I mean, we are in minus 35 dB. That's a good value. Okay. And you can see the real part now is 51.6. If we want to increase, we go near to the center, and here we can reduce this value. Okay? Or if we need to reduce a little more. Okay. Then if you look at this picture, we can say that we have exactly at that point 15 ohms. Okay? Because here, if you see, there is 50 ohms and the imaginary part is 0. Then you can see the result of S11 parameters that we are near to minus 40 dB. That is a very nice result. What is important, the simulation, because with this simulation we define exactly what is the size of the patch antenna. Okay? Because we need this size to be centered in 3 gigahertz. That's the reason before to apply that structure we need to define exactly what is the size of the antenna to work in 3 gigahertz. Okay? Once we did that, we eliminate the port because there is not need the port. Okay? And now we go to the next step. The next step is to add the transmission line of 50 ohms. And as you remember in the last class, we explained that we have here the calculator and we can calculate the transmission line width using this second option and putting here 50 ohms. Then if we put here 50 ohms, we can calculate what is the width of the transmission line. In this case, the transmission line size is 3.051 millimeters. With these results, we go and create another rectangle here, because now we need to put this transmission line, but must be put exactly in the center of the table. Okay? Then remember that this point is the center of the system and it's 0, 0. All this width is $L and all this width is $L. Then if we go to this point, to this center, is 0 in X and is minus $L divided by 2 in this position. Okay? Then we explain to René. This is our system. This is X and this is Y and this is the point 0, 0. Okay, René. Then this is our variable $L and this is our variable $M. If we analyze this point is located in X in 0, but in Y the position is negative, minus $L divided by 2, because all this L, then this half will be L divided by 2. Then this position is 0 in X and minus $L divided by 2 in Y. We need to know this point to define this rectangle. Okay? In this rectangle, we need to define this vertex and this another vertex. These 2 points to create the next rectangle. Okay? Then we go to this rectangle and we need the second description. I mean, we need to put 2 points, point A and point B. This will be point A and this will be point B. What is then the point A? The point A in X, okay? In X is this dimension and in Y is minus L divided by 2. What we know? We know that this width is 3.051 millimeters. Okay? And we can use this variable. Okay? Now, in X, we put minus $W divided by 2. Y divided by 2, because all this width is W. We need to go from the center to this point that is only half. That's the reason this point 8 is minus $W divided by 2 in X, because here X is 0 and we need to shift only this size. In Y, obviously, the position is minus $L. You know, at the beginning, it doesn't matter because we need to define what is the input. Our variable W is exactly 3.051 millimeters. Okay? Then we have defined the first point. We need to define the second point. Then the second point is this one. That if you see here, the position in x is from 0 to $w divided by 2 positive. Because remember, in this position, x is 0. This is negative, this is positive. Okay? And in y direction, we have minus $L divided by 2 minus $y. Y1 we can put because we don't know exactly what is this dimension. We can put any one at the beginning. Okay. It doesn't matter what's value now because you have here this transmission line. It doesn't matter what it is. We have to define what? An input impedance. Then we need to vary this value and define here a real value. Okay? Now, then the position for point B will be W divided by 2 and minus A divided by 2 minus $epsilon. As I told you, this epsilon 1 can be anyone. For example, I can put 5 millimeters. Okay? Then you see, there is a patch to the transmission line. Okay? Now, once we have this, we have to put the port. Then remember, in this case, we don't use a coaxial cable, we use this H port. Then we select this icon and we select this H. And this H is now our port. And we go to excitation. We just do right click and we have a port. Okay. Mr. Torres, where is your computer? But you are the technician. Ah, you don't have time. What happened? A lot of cares? A lot of work? I don't think so. Okay, Aguilar. Which point you are? You are in the same point? Come in. Bring your computer. Yeah, bring your computer. Sit down there. I will follow you. Irina, you are in the same point? How long? You need one semester more? I guess yes. Come on, man.
Guarda mi compo che non è.
Okay.
Hay muchos se pagan.
Ese es adaptador de
Que se adaptó a la link.
Please, I need all of you
No, será.
in the same point.
No revisaba la verdad.
Ahorita vale eso. No se paga, Salam. Salam. Te llamo. Leo Gabardina, te iba a instalar. ¿Quieres que te esté instalando? ¿Qué? 3.5. Pero ahí había un tutorial. O sea, en la carpeta, no sé si les pasaron eso. Uno que te viene con un blog de notas. Yo tengo o sea, vas de router en router, pero ahorita no pasa nada, que vamos a hacer lo que empieza a decir. No, tienes que conectar a la máquina. Una vez que te conectas, ahí sí la abres y ahí vas instalando.
To design this structure, okay, the first step is to simulate the antenna with a coaxial excitation. Why? Because first we need to define in the best way the length or the size of the cable. Okay? Because if we calculate, it was a dimension again, but it's not that we have to use. We optimize the dimension, and this dimension with this simulation was 23.17 millimeters. Okay? How we get this value? Simulating with this instructor. Okay? This position is not really important for this instructor, but it's important to define the dimension of the antenna. Okay? That's the reason. First, we give this instructor. Once the instructor was with good results, I mean, this impedance was in 50 ohms and the reflection coefficient was bigger than or lower than minus 30 dB. We say that the result is nice and good. Once we have that result, we eliminate this port and we go to the next step, and this is the okay? Then what is the next step? Once we have the patch antenna, the square patch antenna, we need to put a transmission line. And the transmission line, okay, the important thing is that this transmission line is next to the patch. There is no possibility to put any hole there. You have to put exactly next. Okay? Then, as I explained you, the length, this one, at the beginning is not important because we need to vary this length until to find a real input impedance. Exactly as you study with Professor Infante. Okay? Then, in the calculator of the software, this width of the transmission line is 3.051 millimeters. Okay? Then we have to define exactly a transmission line with this width. Then remember that in our structure, this point is the center of the structure of the patch. I mean, here this is 0, 0. And this width is L, and this height is L. That's the reason, as I explained you before, this point is exactly the point 0 in X, because here in X we continue 0. But in Y we go down until minus L divided by 2. Okay? And we need to put exactly in this H, this transmission line. Then we need to put this rectangle with 2-point description. I mean, with the point A and the point B to define this rectangle. Okay? Then this point 8 is exactly this position, and this point B is exactly this position, where this length is not really important at the beginning. Okay? We put this epsilon 1 as 5 millimeters. Okay? Now, we need to put here the port, because in this port we need to search what is the impedance, input impedance. Okay? Then, once we put the port, remember that we put the port selecting this icon, that we select H, we select this, and we go there. You are tired. And you. Okay. Okay, then, once we are here, we simulate. Okay, and we go to simulate. Let's see. Now you know, this works in NASA. But here, this is the problem with this. Because you know, everyone uses this.
Ahí no es, ahí no es. Pero de ley tienes que hacer con ecuaciones.
Claro, es que con las funciones no lo puedes mover así, baila así como dije. Help me.
What happened?
One moment, please. I need your help, please.
Quiere gel, no champús.
You are a pro.
Quiere su
You don't have a problem. You are a pro. Okay. Then I repeat you. We simulate and we need to check the result. What result? The result that we need is the input impedance. Okay? Then if we look at here, the frequency that we are interested in is 3 gigahertz here. Then if I change the length of the transmission line, the impedance changes too. Okay? Then let me change this value, I don't know, 8 millimeters. Okay? And we simulate. Okay? Then the value of the impedance, as you see, change. Okay? How these values change? Okay, how these values change? Then Samaniego. I repeat once again. Now we have this structure, this system exactly represent this system. Okay? We have the antenna and we have the transmission line. We have the antenna, we have the transmission line. Okay? Then I don't know. We have these 5 millimeters and we determine the input impedance. Okay? Let's go back here. I will go back to 5 millimeters. Okay? Well, you don't need to watch. You need to listen. Okay? Then the impedance is exactly 43 ohms plus minus J 54. Okay? Then, what happened here? The input impedance with 5 millimeters is exactly 43 minus J 54. Okay? This impedance